Thank you very much. Don't be fooled by my German accent. I'm actually here working in France, in Lyon, so I didn't need to travel far to come here. Thank you for having me. Okay. Do you still hear me? Yeah. Okay. So yes, today I would like to talk about reasoning in and from images, and reasoning means, for me, because the definition of reason, what reason is not an easy one. But for me, reasoning means high-level cognitive processes and working on solving complex problems. And this is a whole roadmap, because this is not an easy task. The only real tool or object which we know who can solve this kind of task perfectly is the human. So my talk will be based on decision-making. So obviously these are things you probably know. We have images and we would like to take some decisions, and this can be a classification into categories, some regression of some continuous value like age here, some decisions. This is not really visible, but this is a 3D environment, and an agent needs to decide whether he needs to go left, right, backtrack, etc. Decide on motor commands, for example, on grasping, robotics. You have input vision and image, and you would like to decide directly which motor you need to put to which voltage. Or the other way around, you go to the domain of images from text. So for example, taking this textual description, a blue parrot with a yellow belly sitting on a branch in the forest, and would like to create an image. So most of these kind of things need some kind of high-level reasoning, some more, some less. For example, here you could say you can cope by getting away with pattern matching. To find a cat, you can detect specific parts of a cat. Here it's a little bit more complicated, right? So you need to grasp high-level concepts, in particular if you want to have some control on the image you want to generate. So how can we do that? Well, lately we did focus our attention as a community on learning, because obviously handcrafting all these decisions is currently out of reach and probably will always be. So we'd like to learn some kind of function h, which takes a decision y based on input x and based on some parameters theta. So this is known. And so there are two things in there. Basically, the functional form of h is what we design. It's handcrafted from domain knowledge. And the parameters theta are learned. The question is, how much do you handcraft and how much do you learn? So as a community, we jumped from here, now probably here, to here. And we'll go a little bit back. So from handcrafting and designing as experts, as computer vision experts, and using mathematical tools, decision functions, since 2011, 12, 13, we jumped into this deep learning craziness, where we throw deep networks on problems, train them on huge amounts of data, and check what happens. And it works quite well. So we plucked this the low-hanging fruits of the tree, and then we found out there is some kind of a ceiling somewhere. We go, to some point we can't go further, right? And there's lots of work recently which has been published on the limitations of deep learning. So basically, in lots of domains, we found out that deep neural networks exploit biases. This is not really a surprise, right? There are statistical models, so whatever is in the data will come out in, garbage out. Now, very often we found out these networks do memorization, so they find key patterns and reproduce them. This is not bad. This is what basically statistics is about. And on lots of problems, this is what we want. We just want to detect patterns and exploit them. But in lots of other algorithms, we would like to go a little bit beyond and do high-level reasoning. So that's what we try now. So the three fundamental problems we have in machine learning is, this is with respect to this problem here, learning this function. So the expressivity, what kind of problems can my model express? So this is the function h, right? If I make it more complex, I can express more complex functions. But it comes with the downside, trainability. If my functions are too complex, I can probably not train them anymore. This is because neural networks are nonlinear models. We use non-convex models, and we use gradient descent to optimize. So this is basically a numerical problem, an optimization problem. But even if I'm perfectly capable of training my network on my data, this means that basically I can train it on, fit it perfectly, have zero error on the training set. The question is, how can I generalize, right? It might be able that my function is expressive enough, it's trainable, but it doesn't generalize. So for people who say that basically machine learning is an optimization problem, these people stop here, and normally I do not agree. So the generalization is an important part here. I'll just give an example where, for example, just taking a neural network and throwing it to data is not the smartest thing to do. So for example, let's take image classification. You want to recognize monkeys. And let's just say we use a single neural network which uses fully connected layers only. So don't do this at home. I perfectly know that we don't use fully connected networks anymore, but let's just imagine we do that. So what happens? Well, basically, whether your monkey is on the left side of the image or it's on the right side of the image, it will activate, it will be on different pixels. Different pixels are connected to the different hidden units, and basically you will train different hidden units according to the position of your network. This is pretty well known, right? So that's why we don't do it. So how can we do that? Well, we solve it by making the problem shift invariant, right? So here I will not use many equations, so there is just one slide with one equation. So we have this operator phi here, which works on images, right? So we have images input, x and y, and phi is my operator. And let's just say I would like to get a shift invariant operator, right? Shift invariant. This is what we want. Translation invariance, shift invariant, same thing. And we also want it to be linear. Why do we want it to be linear? Because basically deep networks are sequences where we alternate between linear layers, elementalized nonlinearities, linear layers, elementalized nonlinearities. So let's just say we want to replace a fully connected layer with a shift invariant linear one. So if we take this thing and we develop it a little bit, a couple of more equations, you don't need to understand them, but basically they're also from Bernd Jene's textbook. If you use linearity shift operator and then you come out with what? A convolution. So basically convolutions are the only operators which are linear and shift invariant. And this is the reason why we put convolutions into deep neural networks, right? This is the only one, because we want them to be shift invariant. This is not a coincidence. So why did I choose this example, which is well known, by the way, obviously we didn't invent this, to say that, okay, deep networks are one thing, but don't apply them in just a simple way, taking off-the-shelf models and throw them on your problem. Try to find out how your data is behaved, trying to find out what properties your data has, and try to put them into the structure, your network with this knowledge. This is called inductive bias in machine learning. So you restrict your class, your hypothesis class of functions, to functions which properly support your data. Your network will work better and will use less training data. So I shift my focus to something else, but it's related. So for example, what else did we want in computer vision? We wanted deformable models, right? Let's take deformable objects. What's the most deformable objects we frequently encounter? People. We are deformable, we are articulated. But even each model, each 3D object which you look at from a 3D viewpoint and which undergoes projective distortion is deformable, basically, right? So if you take this bicycle here and you look at it from different viewpoints, it deforms in 2D space. So how did we do this 20 years ago with these deformable part space models, which were dominant before deep learning, which basically did what? They learned different parts. Each part of the object had its own filter, this guy here, had its own position, anchor position, and deformation coefficient, and then during testing, so we trained this model. During training, we learned the filters, we learned the anchor positions, we learned that handlebars are in the front of the center, the wheel is under it, etc., etc. We learned deformation coefficients, and then when we applied the knowledge to detect whether a bicycle is in the image, we solved combinatorial problems. We checked for all different positions in the image and solved the combinatorial problem, which was costly, right? So this was what dominated before deep learning. Now, do we do that now? In science, not. And the question is, do we as humans solve combinatorial problems to find out where parts of objects are? We don't know, but I don't think so. How do humans solve this problem? They use attention processes, and this is what's now probably the most dominant mechanism in vision, in language processing, in deep learning. So instead of solving combinatorics to find out where things are, we use sequential process to look at specific parts of the data and shift our attention to specific parts. The humans can't do otherwise because we physically basically are limited by time, right? So we look, for example, at specific parts. So if we compare how deformation models and attention mechanisms in vision work, this is a summary of what I just said. Combinatorial problems here are solved, so I check all the different latent positions by solving this equation with respect to the positions here, pi. How do attention processes work? I look at some part in my image, I focus my part on some part in the image, this goes on a deep network. My deep network will output a new location. I will look at a new location, it will process this, gets out a new location, and sequentially I shift my attention to specific parts, right? No point is ever questioned. This is a pretty old paper by DeepMind. Not all attention mechanisms work like this. Lots of them use more soft attention mechanisms where basically you average over positions weighted by distributions, but it's very similar. So you don't ever question a position. Right? Language processing, it's the same. We focus our attention on different words. So in the next couple of slides, I will present a couple of papers and work we did in our group with my students on attention mechanisms and this kind of things for computer vision. And the first application I would like to talk about is activity recognition. So basically, you have visual input, and people are doing something, would like to find out what they do. We can talk about video surveillance, for example, but also protection, computer games, human computer interfaces, etc., etc. And very often we use skeletons, articulated pose only. So we detect articulations. Where are the different articulations of these persons? How do they evolve over time? But very often context is important. So if I find out what these people are doing and obviously why they are doing, it might be interesting to look at other parts of the image, right? So here it becomes a little bit clearer why this lady is running. So there's a fire somewhere, and here these guys are obviously, so that's Seinfeld, these guys are obviously missing a plane or something. So shifting our learning to put our attention on specific parts of the image and video can be important to find out what happens on the actor itself, right? Not only looking on people. So this is work by my PhD student Fabien Bardel, who is in his third year here in Lyon, and in collaboration with Julien Mille from INSA Val d'Or and Graham Taylor from University of Guelph. So basically what we did here, what you see here is glimpse points. Obviously, I don't want to say we in this work are superhuman, but there is one thing we can do better than humans. Humans are restricted by physics. When you look at some point, you can look at a single point in time only, because physically you can't do other things. But this here is an artificial vision process, and you can very well look at multiple points at the same time in the image. So what we do here, we have a video, frames, sequential frames. At each frame we look a certain amount of time, several times, and then we switch our attention to the next one. So I just want to wait for one thing. So you see, when the guy picks up the bottle here, just before he understands what happens, when does it cycle over again? Sorry. At one point you will see a yellow frame. The process looks on the bottle here, although it was not yet clear whether this guy will bend down and pick it up, right? So the model learned that It needs to place attention exactly at this place. And this is a mixture of salience, right? The bottle itself draws attention, and also eventually the guy puts his focus of visual attention down there, etc., etc. We don't hard code that. The model picks it up. So how does this work? So we have here a sequence of frames, and we have a neural network which needs to learn where to attend. It needs to learn how to track attended points, because we have now glimpse points, and it needs to learn how to recognize from a local distributed representation, because each frame now has multiple points, like interest points, right? So how do we do that? Well, we have a recurrent neural network here. So like a normal neural network, but which takes cyclic dependencies over time. So each hidden layer from one time step gets input from the hidden time step before. And this neural network will output a sequence of locations. Each frame gets 3 glimpse points decided, and it does not stop at the end of the frame, so directly jumps to the next frame, which means that context from the last frame can be transported to the next frame. This is the equation here. So this is the hidden state of the network, and I will not go into details, but basically what's important, hidden state, so G here indexes the glimpse points. G0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the hidden state of G is dependent on the hidden state of G minus 1 plus, what is this here? This is what the network saw at the last time step, like a human, right? When you look in a scene, the things you see at instant t will influence what you will look at t plus 1. So this is the glimpse point, the last Einstein, and this is the recognizer. I'll go back to this later. So this creates a sequence of points. And the whole thing looks like this. The RGB image goes in. The attention process is actually not done in the image, but in a feature representation. So we have already a neural network here which extracts features, which have the same temporal resolution, and then outputs a series of points. And the problem is, if you let a network look whatever it wants, it can at one point look at your left shoulder, then look at lots of other things, and 5 frames back, come back to your left shoulder, right? But in the action recognition, what you would like to do is track things. You would like to see where your left shoulder is over time, where your right hand is over time, etc. So if we take this cloud of unstructured points and just feed it into a network, we lose all this structure, right? So what we do here is we have a set of workers. These are other neural networks, recurrent ones, and we soft assign them, each one a soft distribution over this glimpse point. So each worker gets a couple of points. And then we have one model here, a third one, which assigns points to workers, which says the left shoulder goes here, the right shoulder goes here, to this worker, the hand goes here. And this model is also trained, right? All of this is trained. So we get here loss, discrimination, what is the activity class, and the whole thing learns how to put attention and how to distribute these attended points to different workers. It's all learned. We have a couple of other losses, but mainly the main loss is class recognition, and it can also be trained with class recognition only. I won't go into the details of the other losses, but basically even if we train it only on recognizing the correct classes, it trains a little bit lower, a couple of points lower if we lose these other ones, but it still trains. So basically the model, we give it the possibility, inductive bias, of learning how to look at specific places, but we do not supervise it. There is no supervision in looking somewhere, and it picks it up itself, right? I'll not go into details, but when the paper was published, we were state-of-the-art on 2 data sets. Now, it's a year ago. A year is a really, really long time in deep learning. We have been overtaken by other methods, which also use attention. The funny thing here is, when you use attention processes, I'll go back here to my first video. The funny thing is here, when you use these attention processes, you have a methodological part, you model, you think, you try to find out what would you like the model to pick up, but you also have an experimental part. And the experimental part was always very large in machine learning, but now with these deep models learned on massive amounts of data, it gets more important. I forgot to put the slide into, but we have another method, for example, which uses skeleton points. So Kinect basically output, and which puts attention on the different joints, right? We wanted to find out how we can attend more important joints. For example, when you shake hands, then it's obvious that the attention should be put on the hands, right? And the model picked this up, so we learned it on a huge data set of 60,000 actions of 60 classes, the same as this one basically. And then we found out that yes, there are things which we anticipated and which we thought it would pick up, and it did. We were really happy. So obviously when you shake hands, the attention is put on hands. When you put something into the pocket of somebody, an action you do all the time, I guess, I don't know, but it's in the data set, then the attention is put on your hand. What we did not anticipate is that when Kinect produced a localization error, so when Kinect detected the right hand and it was not on the right hand but on something else because there was something right beside you, then our model very often threw away, decreased attention to 0. So the model recovered from errors from Kinect. So it used local appearance to find out that we should not attend there because it's wrong. So this was not intended. We were really happy to see it, but it was not intended. And this is something we now find very often with these deep networks, that we train it on massive amounts of data, it does something, and sometimes it does not do what we thought. It can be a positive surprise, like in this case, but can also be a very negative surprise. In particular, for example, in language processing, you had a couple of surprises when language tasks were solved very, very easily, and people found out that, well, basically just picked up a couple of keywords, and these keywords were highly correlated to the answer, and it didn't reason at all. So some people call this now the Clever Hans effect. I don't know if anybody heard about this. No? That's from Germany from the last century, when somebody presented a horse which was able to count and to do arithmetics. So basically you ask the question, what is 9 plus 3? And Hans, the horse, would like 12 times bump its foot on the air, and it always worked. And a couple of years later, they found out that basically the owner of the horse did some sign, I don't know, they did squeeze it, whatever, but anyway, so the owner did the calculations and showed the horse in a really invisible way how long to put the feet on the ground. So basically the horse didn't solve the equation, and this is now the effect we put, this is the effect, the name we use for effects where deep models in machine learning seem to solve problems, but they really do not. Another example is people tried to control an oscilloscope with reinforcement learning to optimize some circuitry. And in reality, the oscilloscope picked up signals from the computer nearby, which was on the network and which drove the whole process. So the network basically cheated, and it worked perfectly well, but not as they thought. So let's continue. So basically here, what we try to do now in our group, but also obviously the community, is to find out how we can create models which reason, which go closer to reasoning. This means creating data sets which limit biases. If you have biases in a data set, it will pick up the biases. So we need to work on data collection, but we also need to work on deep networks themselves. So can we create models with structure which limit the amount of memorization and which increase the amount of reasoning we can do? The next work I would like to briefly present is relational reasoning. So here this is work also with Fabien in collaboration with Facebook Paris, and Greg Morey from Simon Fraser University, and Julien already mentioned before. So what we want to do here is egocentric activity recognition. So you have a camera somewhere on your head, you would like to detect what kind of recipe you're cooking, what kind of thing you do. So this is highly dependent on objects and object masks. So what we can do here is we can run, for example, mask RCNN, an object detector, get all the different objects, etc., etc., and then find out how they behave. So one thing is we would like to find out what kind of objects are not only correlated with each other, but correlated to the tasks. We call this relational reasoning. This has been addressed by the computer vision and learning community for a long time with graphical models, HMMs, Bayesian networks, etc., etc., and recently with graph neural networks. So basically what you do is, I will skip the equations, you put the descriptors of the objects into, you concatenate them and put them into a into a nonlinear function, so some kind of MLP or something, which outputs a vector. You sum this vector, and this is your output. And basically, the network learns to, in this projection, to model the interactions between your different objects. So you can embed this into a huge neural network. So here our video comes in, and we have 3 different parts. We have the object mask detector, mask RCNN by Facebook, which gives us the mask. At the end here we have the activity loss. So this kind of activity we have, right? Then we have a normal Bayes network, which does activity recognition, spatial, temporal boolean, recurrent neural network. So this is pretty well known. And the middle head here basically takes the objects, pulls features from this feature head here, which shares parameters with the activity head, has a graph network in here, basically, which checks for all the combinations of objects, some recurrent network to model time, and output the activity loss. The nice thing we can do here is that we can check, for example, we have 2 classes now, 2 types of classes. We have the activity class, like person-book interaction, this is what we want to recognize, and we have the object classes, right? There are different classes. We want to optimize classification error here. So what we can look is, these here are correlations. So for this activity class, person-book interaction, we have strong correlation between all these different classes here. When we check here what kind of combinations have a high norm of the graph network, then we get not only correlated classes, but the classes which are relevant to the task. So for person-book interaction, we need a person, a book, and eventually background, unfortunately. So this is things which is not supervised, right? So we don't supervise this at all. This is picked up by the network. And it learns to look at these combinations exactly for this class. Do I still have, 10 minutes or so? Yeah. So the last thing I would like to talk about is image and control. So until now I talked about activity recognition, so basically it's computer vision, but a really, really hard task, which made a couple of people, including me, move a little bit from computer vision to robotics, is that, well, many people say vision is solved, and we all know this is not true. But lots of sub-problems in vision are not solved, but close to being solved, right? A couple of things are missing, but there are lots of many, many more problems waiting in robotics and perception for robotics. And one of them is obviously autonomous driving. We still have the cars on the road, right? It's still not solved and probably will not be for a couple of years. So what you do in this case is here you have some camera, some sensor, some LiDAR, something which measures perception, and you would like to control the gas pedal, the steering wheel, and stuff like that. So your observation here goes into an agent, and the agent outputs some kind of politics. It's called in policy, sorry. Policy, it's called in reinforcement learning, so policy P, it's distribution over my action, eventually some kind of value function. If we stay in the framework of reinforcement learning, it could be anything, but here, let's talk about reinforcement learning. So this agent here needs to reason, right? The obvious thing to do is to just put a neural network in here and optimize the thing. It's not so easy to optimize because we can't supervise the actions mostly, right? We can do imitation learning, so we let people drive and learn to imitate. It's called imitation learning, then it's easy. but it has its limits. If you do reinforcement learning, then you basically optimize some kind of feedback. Did you just crash the car or not? Well, if you crashed it, you're not good, and you should update your policy. But what kind of policy? The last millisecond? Probably not. So which action in the past do you update? It's called the credit assignment problem, and this makes the task really hard. So we need some agent which is capable to use different losses, reward, self-supervision, intrinsic motivation, curiosity. This is what the community is working on right now. And so this agent also needs some kind of memory, right? So when you guys drive, when we drive, we have memory. We have memory on what just happened. Did I just take a left turn? Did I just take a right turn? But also memory on the task itself, right? So if you go to the bakery, you need to know the path to the bakery. So you have some kind of memory. Is it metric? Is it a tensor? Is it a graph? We don't know. I think for long-term problems, mostly it's topological memory, some kind of graph. You don't have a metric memory of your city in the head, but you know that at some junction you need to go left, at some junction you need to go right. So that's basically topological memory in graph form. For other things, taking, for example, a glass of beer or something, you probably have a metric memory. Don't query a graph to take your beer. So it's probably a mixture. And anyway, this spatial representation is learned. It's learned from what? We don't know. Reinforcement learning thinks it's feedback. Every time you hit something, you say, oh, next time I do it differently. But it's also curiosity. It's also lots of different things. Humans learn from different sources. So until now, we were occupied with reward and reinforcement learning, but we quickly found out that reward alone is a learning signal for all this mapping between input, visual observations to memory to policy. It's not good enough, right? So what do? We put constraints in there. Geometry, topology, semantic stability. So this is the link to the other talks or the other things I presented today. Don't go to the direct approach, just feed this into a neural network and find out what happens. It's not working so well. So how do we solve this? Well, we have currently these different methodologies, purely geometric approaches, which basically create maps. They use a LiDAR, use geometry, a little bit of estimation, also machine learning, but basically to find out where are the obstacles, let's put them on a map, and puts this into some kind of planner. The planner is probably not a neural network. It can be, but not necessarily. You can do shortest path and other sophisticated methods. On the other hand, you have these purely learned methods. They take these observations, images, put them into neural networks, and optimize reward. Now, these things do not work, and they work well. And these things do not work, and they work well. The question is where? These things are, in theory, more powerful because they can pick up highly semantic regularities. They just don't transfer to real data. So I didn't see a reinforcement problem in real life yet solved by reinforcement. These guys here do work very well, and they're implemented on real robots, but they're just not working well in the sense that their capacities are not really good, right? They don't pick up high-level reasoning from data. They need to be handcrafted. So if you want to make them detect an obstacle, you train them on the obstacle. What can I do here? For example, I'll give one example. So what we do here, before I skip over this, we want to go take these methods, push them into this direction, adding semantics, make them a little bit more flexible. What we want to do here is take these methods, add constraints, make them work, make them more sample efficient, right? Because normally we learn them on billions of observations. And that's not possible. And mostly simulation, obviously. You can't learn on billions of real measured images. So the work I will present here really briefly is of this type here. So we take these methods and try to put inductive bias in there. So how does a traditional reinforcement, deep reinforcement learn method work? So these are the kind of models which are used by DeepMind, OpenAI. They have worked a long time on these. So basically you have an observation at time t, you put them through some kind of perception module, which is a really easy CNN, easy in the sense, not many layers. If you don't typically put a ResNet in here because it's just too complex. So some easy convolutional neural network, you put this into a controller, and the controller outputs some policy distribution or reaction. If your problem is fully observable, like chess, like Go, so everything in one observation, you have the full state of the problem, then you need only this. But autonomous driving and robotics is not fully observed. The history is important. So basically what you add is some kind of memory here, some hidden state, and the controller updates the hidden state over time. And your hidden state allows you to work on some kind of memory related to the history of observed images you saw. The hidden state here typically is not structured. It is a vector. Typically, I don't know, 64, 128, 512 values, and everything is in there. So if you learn an agent, a robot, to drive around in a scene and make it navigate, and it needs to remember where things are, then all this needs to be encoded into this memory, right? So if you make your agent look at some object, see that the keys are there, right? So typical, very, very easy, no, not easy, very interesting application. Please, robot, find my keys. Where are my car keys, right? The robot needs to run around. So if the robot is trained on that and it navigates in your house and at one point it sees your keys, hopefully it will store them so that it will not search them when you ask it to. So if you try to solve these kind of problems with deep reinforcement learning, then your car keys need to be in there, somewhere here in a flat vector. This does not make any sense. Robotics does not use flat vectors. Robotics uses maps. Structured information. So what in our work we try to do is structure deep networks and add maps, but not pre-calculated maps. We don't calculate maps, finish them, and add them as an input. That would be too easy, and we don't like easy. So we structure the network such that it creates a map itself. So this is how it looks like, and this is work by our student Edward Peaching, who is in now second year since a week. And in collaboration with Gilles Dibongoy from INRA Chroma and Olivier Simonin. So our network here, which takes the observation, is a perception model which satisfies projective geometry. So basically, it maps the image here into a plane, into a bird's eye viewpoint plane, right? So how does it do that? Well, by satisfying projective geometry. So we think the camera is calibrated, it is calibrated, and these guys here are mapped here, these guys are mapped here, these guys here are mapped here, and everything which is behind us is not mapped, so this guy is not mapped. But the important thing is, it's a mapping. It is still a neural network. So basically, what is mapped is learned. So this mapping is also a 3D tensor. We have multiple planes, 16 for example. So we have 16 values for each position on the map. And the thing is also when the agent moves, it moves with. So if you turn left, the map turns left, etc., etc. So this is how it's integrated. We still have the same module as before. We add this perception network. We still keep the other, the hidden state, the flat hidden state. We add this perception module in here. There's a differentiable affine transform. Differentiable important because we learn by gradient descent. And so when the agent moves, the map moves with the agent, right? What is on the map? We don't know. It's learned by reward. So we still have reward coming in here. It's not drawn, but we still have reward. And the error of the reward, or the maximizing reward, is backpropagated from here down to here, but also here. And basically the agent learns to find what is called in cognitive sciences affordances. If something is meaningful to the task, it will pick it up and put it on the map. If you're rewarded for picking up the keys at some point, it will pick up the keys and put it on the map. If the keys are not correlated to a task, I'll just ignore them, right? So this is more powerful than creating maps in a handcrafted way, because the network decides what's on the map. I will not go into the equations, but this is basically what I said. So basically you have an affine transform which updates the map. You need to do the inverse projection, and then you need to read. So basically the controller needs to read the map. It needs to learn what to put on a map. Yeah, 2 minutes. Let's to read the map. So you can either have a global read here or a query attention. What does this mean? It's again an attention mechanism. So the controller can say, I don't want to look at the whole map. This is too complicated. The tensor is too big. Please check whether the keys are inside. So how does this look like? We have a query generator, which takes the hidden state, takes the global read, outputs a query, and this query vector is checked against the inputs with the L2 norm or something, and then we get the output. Well, just before I finish, visualize this. So this is a very easy task where the agent needs to run through a maze. So this is VizDoom, for those of you who are old enough. Doom came out in '93, right? Now we don't play Doom ourselves, the late neural networks play with Doom. So we put a couple of objects in there, and the task here is to pick them up in a specific order. If you don't do anything, you die after a certain amount of time. If you pick up an object and it's in the right order, you get high reward. If you pick up an object but it's not the right order, then you get lots of negative reward, right? So, and this order is not known to the agent. He needs to learn it, right? So what happens here, this thing here, the blue ball, he sees it, it will not go there because it knows, or it learned that I now first need to see the health pack and I pick the health pack. After I pick the health pack, I'll need to pick up this thing. It learned to pick up this thing in here. What you see here is the PCA, so the 3 principal components of my 16-dimensional tensor. And when I say it picked it up here, then I can ask you to trust me, but I would not do that. So instead of trusting me, I will show you that it really puts it there. How can I tell you that? Well, basically, a couple of frames later, it picked up the health pack, right? Now it needs to find the blue ball, and it draws its attention to the blue ball. So this thing here, this is the attention vector. Clark, the network says, please give me that. So this is the effect of the query vector. It outputs a query vector, and this is the minimum. This is the minimum distance. This is the location which has the minimum distance to the query vector. So this is the kind of almost proof that the network now searches for the blue ball. It attends the place where the blue ball was when it saw it, right? Goes back, still attends it, and then when you turn around the corner, now it finds out it is in clear view. I don't need to attend my memory anymore because it's in my view. I don't need to query the memory. The attention drops, right? So, and when you train this, so this is the baseline. This is a normal neural network, and this is the one with this affine memory. It gives higher return on this kind of tasks. I will finish now with the conclusion. So the problems we have to solve in machine learning are expressivity. We need to model symmetries and invariances in our data. This is really important, not just throw networks to your data, check what the symmetries and properties are. We need to find trainable functions and make them generalize. And so we changed a little bit as a community. Between the 60s and 2012, we handcrafted features. We went away from that. For 4 years, we handcrafted architectures. We found the best deep networks for specific tasks, like ResNet and stuff like this. And I see now, this is my point of view, basically, so I see a trend now, instead of handcrafting architectures, let's handcraft data flow, right? Let's put geometry, causality, and attention into models and handcraft how the network flows, makes data flow through it. Thank you very much.